Hey, can you hear me? Well, a pleasure to be here on a Saturday morning. Thanks everyone for being here. I'm going to talk about Cerberus and give an overall brief overview of its capacities, what it does and what it cannot do. Oh, closer, okay. Yeah, what it can do and what it cannot do and what it will never do. And start with a very simple points. And I think there are basically two things I would like to emphasize for Cerberus. And, usually when people talk about parametric retrieval, they say, okay, this guy is going to tell us exactly what it is inside those atmospheres with, a 100% or that kind of certainty. And it's true for all retrieval. We have one interpretation of the data. We make a lot of assumptions, and the important thing is to never forget the assumptions that we made behind. And this is especially true when you're talking about something that is extremely far. We don't have in situ. We don't have instruments that are close, that are really inside the system. We are indirectly probing the content of those atmospheres. So whatever we derive, we derive it with making a lot of assumptions. And a very important point when we make that is the formalism we use. And there's a lot of things in Excalibur, and you'll see the word Bayes and Bayesian methodology, Bayesian method use, and those are the methods that that reminds us the most that of all the assumptions that we made. So Cerberus, there are three parts in Cerberus. For one models, that's how we built the basically from the atmospheric profile, how we model the what we will confront the data with. So how we will compare the data with the model. Parameter constraints, that's how we're going to retrieve the parameters that went into the model. So it makes use of MCMC chains. And the model comparison, how we compare one model to another, how we separate families of model. And the model comparison is the first place I'm going to start with, because it uses Bayesian formalism. And in the Bayesian formalism, it's really hard to forget the assumptions. It's usually this term that is just impossible to evaluate. The probability of your model to describe your data properly. Usually you put that as a 100% possibility, because of course you build this model, you are sure of yourself, you think that your model is going to fit those data. But in reality, this probability is not 100%. And a lot of the time you forget about it. So model comparison, there is a whether you use a chi-square, which is the frequentist approach, or the Bayesian formalism, an evidence score. The main question is, how do I compare one model with another? And not all models have the same numbers of free parameters, so you want to be fair. You want to penalize a little bit more the models that have a lot of degrees of freedoms compared to the ones that have little numbers of degrees of freedom. And the ingredients for that are always the same. So you will always find something in this in the matrix that are the residuals between the data and model, so the first point. And that's common to both metric. You have some kind of estimate of the noise, and you have also an estimate that's going to penalize the models that have a large numbers of degrees of freedom. And that you would think it's easy to evaluate, but in the case of relative transfer code, it's not that easy. Let's take a very simple example. Like, let's say that I have a friend, Jay, and Jay is that kind of guy who comes up with theory. He really likes theory. He really likes to make things extremely accurate. So he comes up in my office and say, hey, you have this haze model, and this haze model, you've been doing it all wrong. I know exactly what you're going to do. You're going to correct it, and instead of taking one size for your all haze particle, you're going to start to use a haze particle distribution, which is actually a very good idea. The thing that my friend Jay forgot is that I'm working with HST data with error bars that are huge. So you have to be a little bit cautious when you start to develop your model. You don't want to put tons of extra parameters that will never be probed. So particle size distribution, okay. And then he tells me, what are you using for your scattering law for your haze? And I say, I'm just approximating. I'm saying all my haze, they scatter, that they are in the Rayleigh regime, kind of the approximation. He says, okay, look, you're just a beginner. Let's forget about it. First, because haze, they can be fractal aggregates. So now you're going to use the T-matrix approach, big things. And the numbers below are the minimum degrees of parameters that my friend introducing every single time for every single particle. And he finishes up with the last point. Look, this is my haze density profile. And, you have to come up with something that is a real density profile, because the haze can be localized at very specific pressure layers. It's not completely uniform, homogeneously mixed throughout the entire atmosphere. In theory, my friend Jay is absolutely right. And that's how things should be properly done. And hopefully, that's how things will turn and will evolve with GWST data. But at that time, I was still working with HST. So in other words, my friend Jay, in his model, has about 500 parameters. I kind of multiplied everything together. And the day after, long time after, came up with this model. That's the dashed line here. The thing I didn't realize when I first saw this model is the units. There has this little factor on the top that I didn't realize. So I said, okay, I'm going to try to put that with data. And if I put that against the data, what I obtain is this line, this flat line, this big flat line. 500 parameters for Jay's model that can all be resumed, that can all be condensed into this model here that I come up with. So basically, your S model is just a constant across wavelength, and the numbers of parameters of my formulation is 1. So the question is, for the exact same model, at least on the data, what is the right number of parameters to choose? And for every single one of you that has done model parameters and tried to reach an understanding of what is the total numbers of degrees of freedom that I should use to penalize my model, here's an example of 2 models that are exactly the same, but with numbers of degrees of freedom that are completely drastically different. And this whole example to say, okay, what we really care about in our code and in our model in exoplanets is some kind of this effective number of degrees of freedom. And that's something that is very, very hard to compute. You can approximate it. There are techniques to approximate it. Basically, you walk around the solution and you try to estimate if your parameters still have an influence on your model or not, according to the noise, to some noise propagation. That's one way of doing it. In other words, you estimate the local Fisher matrix of your model to estimate your numbers of degrees of freedom. And of course, in the case of the haze model of my friend Jay, that would be basically 0. So one parameter of your model, you will remove the average. That's basically 0 degrees of freedom. There is another thing that That's very common mistakes when you start modeling things, that the numbers of parameters, whenever they are larger than the number of your data points, you're in a bad shape. And it's obvious here in this example, but how many times I've seen people with light curve that have 30 data points and their instrument model have more than 60. That's a problem. Yeah, the last point I wanted to discuss, and that will serve as a transition to the next slide. The data quality should guide setting appropriate priors. So your beliefs or your assumption when you're doing a parameter recovery, but also build reasonable parameterized forward model. So in that case, reasonable means forward models that do not have 500 free parameters. The forward models that are built in Cerberus, there are two categories. One category which uses the standard parameterization. Basically you put everything in solar abundances. You tweak a little bit of nodes, and you let everything equilibrate according to a thermal equilibrium argument. Right. So that's what everything is doing. And for HST is been doing an incredible work. I mean, it's when you're looking at ultra hot Jupiter, that's the first thing, that's the first approach that you're gonna do. The other thing that the other family of models that Cerberus has is what we call some kind of free retrieval. So instead of taking those free parameters, transforming them into volume mixing ratios of your preferred molecule, water vapor, carbon dioxide, or whatever, you were trying to measure directly the volume mixing ratio of those absorbers without any tie to chemistry, which is extremely dangerous. You have to be very careful when you do that, but that is called free retrieval. So you have an independent measure of, let's say, CO, water vapor, CO2, and then you let the data tell you whatever you want. And when I talk about model comparison, basically, I'm comparing this approach, which is very simplified, and in most of cases does not work very well. And this approach, which has no real physics behind, so also extremely dangerous, but Bayesian by constriction will fit your data. So you have to balance. The two. And the initial questions when we started the study with the HST and G141 on all those forward models is, so we have a unique data set in there that has been reduced in a very unique way. It hasn't been fine-tuned for every single target in there. And we know how important it is, especially for those data. I don't know if you have seen HST data, but it's not really nice to see before the calibration, before they've been reduced. There are systematics everywhere, and the effects of the systematic is huge. So the data reduction and the way you're going to reduce the data is going to influence a lot your result. And yes, the spectrum in some cases is different from what has been published before. And and starting from this, the real question that came to mind is, okay, with this new data set, how, if I choose to interpret this, with the usual argument, as a water dominant signature, as a thermal equilibrium, what is it going to say about those frequencies, about the metallicity, C2O and N2O? And in most of cases, you can just constrain one of those parameters, basically barely the metallicity. The other questions, once you've done that, is okay. So now let's let the data speak for themselves. let them say whatever they have to say, knowing that there is no real chemistry behind. You have to be extremely careful of the result. So we're going to build models that let the data explain themselves, but still are very close to this first initial solution there that is driven by equilibrium chemistry. And we're going to call this category of model, a slightly distorted, from the equilibrium plot, disequilibrium chemistry, but still in family, or most of it, of what would be the content if everything was in thermal equilibrium chemistry. And that's with the spirit that we try to interpret and compare those two big families of models. And I think that the real question that we wanted to answer is there any hints in those HST data of something that is not fully in a thermal equilibrium, or in other words, that is not entirely dominated by water or entirely flat, dominated by, who have no spectral modulation at all. And going from HST to Ariel, things will have to change. And I believe that the code or retrievals and retrievals by themselves, they started to change already. We'll have to adapt to this wide wavelength range where we're not probing just one absorbing species anymore, but multiple ones. And we have to tie all those quantities, all those volume mixing ratios of different species all together. The only way to tie them is through robust chemistry behind. So tie the temperature profile to gas and condensate and condensate formation chemistry. Or in other words, or some kind of term that is really fancy and used at the moment is self-consistent chemistry or self-consistent modeling. I think that's where we want to go when we probe more than one or two main absorbers. The other point is to keep this open-minded and let the data express themselves point of view on the back of our head, and keep doing this comparison between the fully motivated, chemically motivated models and the models where you let the data explain themselves. Doesn't mean that one is better than the other, but keeping an open mind to at least compare and give a chance to one model or the other to express itself is the spirit that we're going through. And all those points, of course, have a strong drawback. They are all extremely slow. We're using Monte Carlo Markov sampling, and having a full chemistry inside the code instead of a very simplified version of it is going to take time. And Monte Carlo Markov shell sampling by itself is a process that takes a very, very long time. In Cerberus, the sampler that we are using is a Metropolis Hastings sampler. That's the most basic, not biased sampler. What I mean by not biased is that when you start to change sampling for samplers that are going faster, you are destroying, you are using rules and shortcuts that are not within the Bayesian context. It doesn't mean that they're wrong. It doesn't mean that you should not use them. It means that you should use them knowing what they do and in what context they are not biased. And the problem is, most of the time, people don't. Let's take this first example here. When you're using a nested sampler, people use nested sampler without passing it the very crucial information that is needed for the nested sampler. This is the covariance of your model, the covariance matrix of your model. If you don't feed it that, it cannot build properly and imbricate the the nest altogether. It's going to be the hierarchy of your models. Well, what it's going to do is going to give you very nice posteriors. It's going to build very nice chains. Everything's going to look Gaussian, but it's very far from what it really is. It's just a biased solution of your sampler. And let's take another example of where we have to be careful, especially in those kind of models, on how we interpret the chains. Most of the time, the way you interpret the chain is, I'm just going to take the median sample, the median of the median of the chains, the median of the sample values, and it's going to give me my best solution. So let's take this example here, completely made up. You want to prove this very simple physics law, x squared. You're going to generate some data points centered around 1 with some noise. So what you're going to have at the end of the day, is just one parameter, not even a correlation plot. Those are PDFs, probability density functions. So you're going to have one probability centered around -1, and another one around 1, which is, just basically the answer to x squared equal 1 with some noise. If you take the median, just the median of this chain, the only thing you're going to find is that your base value is 0. And it's fairly obvious in this example, but how many times I've seen correlation plots that are absolutely not Gaussian, that have multiple modes in there, and people just lay down median of my chain without any caution, without even looking if their PDF, marginalized posterior distribution function, probability density function, is nearly Gaussian or nearly symmetric at all. That's something to think about when you're looking at your marginalized PDF. And another success of the nested sampler is that usually, if you don't set things properly, the PDF looks Gaussian. So people are happy. But the problem is it looks Gaussian because you didn't set up, you didn't initialize your Fisher matrix properly to start with. So it just goes into a solution, thinks it's a good solution, and stay there. All right, more than often, if your sampler isn't completely distorted, yeah. So that's what I was saying. So if you don't, the case of the nested sampler, you should have, in most of cases, for the radiative transfer model, you should see those multiple modes showing up, because we already know that the way we parameterize it, the most common way we parameterize atmosphere, parameters talk to each other. There is crosstalk between amongst parameters. So yeah, you expect your posteriors to be not Gaussian normal at all. If you have posteriors that are perfectly Gaussian, that's where you should ask if you've done something wrong. And the third point that I will emphasize is it is not wise to code the median value of your sample as the most likely estimate without understanding, without taking a look at least at the shape of your marginalized PDF. Again, a few concluding remarks for Cerberus. I think it's a code, it's a tool that is evolving and that will still evolve in preparation for Ariel and case. And there are a few points and a few challenges that this code, that this approach will have to overcome. One of them, and I think it's common to all retrieval code out there, is the computational time, the CPU time. And that's tough. So if you have an idea, if you are an expert on CPU time, if you want to help, you're more than welcome to give us some idea. Teach me, yeah, teach us how to do it. In terms of forward modeling, I think really, real ties between chemistry, I mean, gas chemistry, condensate chemistry, and TP profile. All those links and interaction should come together. And, so far, because the cost was so high to compute those forward model, we had to to build those oversimplifications ourselves, assume a constant temperature profile for the recovery and so on. I think that time, know that we're working on such a wide range of wavelength, we cannot do that anymore. We have to work with grids. We have to do the recovery directly on fully chemically motivated model. And to do that, it requires a very strong interaction between people who are recovering parameters and chemists who are doing, some fully consistent picture of the atmosphere. So yes, grid in a strong interaction between chemists and retrieval people. And on the last point, exploring solution for planetary systems that have widely different physical properties. That's one of the most challenging things when you're dealing with thousands of targets. They won't be all ultra Jupiter. They won't be all super Earth. There will be a large and vast variety of targets in there. And how you will interpret them, how you will set up your priors for parameter recovery, that will change for every single target out there, depending on those physical properties. That's it. Thank you.
So are there any, so before I ask for questions, so that is a super important lesson for everybody is always to remember that your Gaussian statistics are not necessarily representative of your distributions ever. Okay. All right. So are there any specific questions for Gael? Yep, see one. Ellen, are there any in line? I didn't see any when I looked. Okay.
Yep. Thank you for the presentation. So my question is, so Cerberus is the part of Excalibur that is responsible for the retrievals, that is, right? I mean, the MC models we are doing with Cerberus inside of Excalibur, is it? Okay, so we have more than one option inside the Cerberus to do the retrievals. So when I have that, just to be sure, when I compare the models and I have to choose the best one, I more than use the chi-square parameter.
Okay, wait.
Okay.
All right. So you have different options to do your parameter retrieval. I didn't say there was completely in different options. You can choose your sampler. You can choose to do the metropolis testing. You can choose to do, other fancy methods to go directly, more directly to the point. But it does not support right now completely changing the sampling method or completely changing the approach. If you want to do a frequentist approach and, build your chi-square there and try to minimize your chi-square, that's not something that's implemented in Cerberus right now. The spirit is more, we are trying to explore the maximum of the parameter space without taking too much time. The method that is appropriated for that is MCMC.
So the best option to compare the models should be the chi-square, or
I mean, if you
analyze everything.
If you're asking me, I would say the best option to compare models is evidence, and it's tied to the chi-square, partly tied. It's proportional to exponential minus chi-square, basically.
And it is such a big problem if I try to run all the options and see what's happened, or just try all the options and compare all the corner plots.
I think, I mean, if you're curious about how it works, that's definitely what you should do, yeah. And see if solutions converge, see if solutions agree with each other. You know, I've heard so many times, I don't understand why my nested sampler gives me different answers when I run it on Monday and when I run it on Tuesday. You know, and it's and sometimes you know, as I emphasize, it's just that you don't use the tool the way you think you're using it. So it's always yes, it's always instructive.
Thank you.
Thank you, Ellen.
Hi, thanks for the talk. So in nested sampling, in particular in packages like Dynasty, they allow for dynamic nested sampling where the amount of live points is actually changed as you proceed through the motions. And so is that something that Cerberus does in order to try and speed things up, or have they considered that?
No, actually, Cerberus right now, as I've chosen to stuck it with the Metropolis Hastings sampler, the slow version of the sampler, and the safest one. I do not use any trick to accelerate the sampling.
Well, it might be worth looking into. I presume that there's a parallelization built in, and that's able to be run on.
There is, yeah, there is there, but the chains do not influence each other.
All right, thanks.
Hi, I was just wondering, I guess it's more in just the retrievals in general. Is it possible to use like a Hamiltonian Monte Carlo or in future, or like what kind of challenges would that involve if you wanted to do that?
Yeah, that's indeed an option that is implemented, and you know, it's not Cerberus by itself. It's the software or the software suite that Cerberus is using, which is PyMC3, that has this option inside. Yes.
Okay, are there any other questions? Okay, well, let's thank Gael. Thank you very much.